Section 4.5, isosceles and equilateral triangles. And what we're going to do is use and apply properties of isosceles and equilateral triangles. These postulates and theorems and properties are those that I kind of think are common sense properties. When you look at a triangle and certain things are marked, you can kind of automatically kind of know what those answers are. So I feel like you're going to think this lesson is way easier than the last few have been. So first we have to go over, what does an isosceles triangle look like? There's a vertex angle. How do you know which one that is? You look for the two angles that are the same. It's not that one. Okay, so here the base angles are the same, these two. So the vertex angle is that other one. So it's the one that's a single angle, not the one that is duplicated. How do you know otherwise how to find out what these are? If these two legs are marked the same, kind of look opposite those two. So if you have only two sides marked and no angles marked, that's how you find out which ones are the same. So with this one, I found this leg matches this one. So this one goes with this angle over here. Sorry. And this one goes with that angle over there. So it's always about opposite. The side goes with the opposite angle. It's not that they're the same, it's just that they go together. So the two legs that are the same are called legs. The other one's called a base. And the one that is opposite the base is the vertex angle. So the first one, and I'm just going to read through these right now. You guys can copy them later. Theorem 4.3 is the isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite those angles are congruent. So basically what I just told you is in this theorem right here. So look for the two sides. The angles opposite those are the angles that are the same. The converse of that, if two angles of a triangle are congruent, then the sides opposite those angles are the same. So the converse of the isosceles triangle theorem says if you know which two angles are the same, you can go opposite those. So this one will be the same as that one. Okay, and it's all about opposites for those two. One of them you're given the sides first, that's the regular one. The converse you're given the angles first. Okay, so look at problem 1. It looks like okay, there's the picture. I'm going to make it a little bit smaller. Okay, so in the picture, so if you're copying, do that later. In the picture, we have this small triangle, ADE. We have a big triangle, ABC, and we have some things marked. So is AB congruent to CB? So they want to know, is this one congruent to that one? What do you think? Yes or no? I have some yeses. So basically what you're going to do is ignore that little triangle that's inside. You're only looking at the big one, and I'm looking at this angle A. This one gets paired up with that one, even though it goes outside that small triangle. This one gets paired up with that one, and if the angles are the same, the sides have to be the same as well. So we're going to say yes. When you're given the angles, is it the regular theorem or the converse that applies? It's the converse. Converse of isosceles triangle. Is it theorem, I think? Okay. So is angle A congruent to angle DEA? So angle A is this one. Angle DEA would be that one. What do you think about that one? I'm only looking at the small triangle this time. We have two sides marked the same, right? This side right here goes with that angle. This side right here goes with that one. So yes, they are the same. So this one would be yes. And this would be isosceles triangle theorem. So if they have to give a reason, just state the theorem. If it has a name, use the name. If it doesn't, use the number. Because there are a couple that just have the numbers. Okay, theorem 4.5. If a line bisects the vertex angle of an isosceles triangle, then the line is also perpendicular to the bisector of the base. There's a lot going on in that theorem right there. I'm going to make this one a little bit bigger again. So if it bisects it, so this line right here bisects the angle, that means it makes those two angles the same. Okay, it also says it makes it perpendicular to the base. That makes those two right angles. And then it also bisects the base, which makes these two parts the same. Now, if all that is the same, don't you think everything else is the same too? If you like fold it directly in half, that angle A and that angle B are going to be the same, and everything else about it. So here's an example. What is the value of x? So in this one, is BD a bisector? Does this thing bisect anything? Bisects the angles, right? So this one right here is the same as that one right there. And when that happens, you have a right angle here, and these two parts are the same. Is this the same as itself? Yep. So we've got a lot going on that's the same in that triangle. So we also have this side congruent to this one. So this side right here goes with angle A. This side right here goes with angle C. So is everything pretty much the same? Yeah. So think about that line being just like a piece of pizza or something, and you just fold it directly in half. Everything about it's going to be the same. So what is the value of x? X is an angle. The 54, I believe, is that angle A at the bottom. Sometimes they put these things out in the middle, and you can't really tell what it's supposed to be. Yes, it's angle A. So 54 goes with A. So how much is angle C? 54. So measure of angle C is 54. And basically we need that to find out how much that x is. So if 54 is one angle, 90 is another, all three of them should add up to, and I'm going to use x instead of b, 180. So as long as you're looking at angles, remember they all add up to 180, and that's going to make it 72. Okay, wait, I did mine a little different. No. That's going to be 36. So 10, yep, that works. You could do this one other way as well. I'm going to show you that in a second. So I get angle 30, or measure of angle x is 36. One other way that you could do it is like this. This one right here is 54. This one right here is 54. How much would that whole thing be? You could just do the large triangle if you wanted. That would be 72. But we know that x isn't the entire triangle, it is split in half. So if you divide 72 in half, you get 36. So small triangle is what I used first, which I think is probably what you guys might do, but maybe not. Most people, when they do these, they only look at the small triangles. They don't look at the big one too. Even though there's two small ones, there's one big one as well. So either way would work. Just make sure that you half it if you're using the big one. The next couple of things you'll have to write are called corollaries. If you were looking ahead in your book, you do have to write them down. They're just things that help you figure out certain things. They're the same. You can use them as reasons. You know, they're the same as a postulate or theorem. So a corollary is a theorem that can be proved easily using other theorems. You can use it as reason in proof. So just because it says corollary doesn't mean you do it like use it any other way. So there are two of those. One is a corollary to 4-3, the other is a corollary to 4-4. If a triangle is equilateral, then the triangle is equiangular. So if you know that all the sides are the same, using that opposite thing when we use it's kind of like using the isosceles triangle theorem. If you know a side is congruent, you look at the opposite angle and you can show those are the same too. So if all the sides are the same, this side would go to that angle, YZ would go to X, and XZ would go to Y. So that means those angles are the same. The other one is basically the opposite. If you know that all the angles are the same, all the sides with those will be the same. So always think opposite and you will be okay. All right. What are the measures of angle AB and ADC in the photo? So we need, I'm going to change my color here. We need A, we need B, and ADC, this one right here. So we're looking for all those. So when I look at angle A, I'm looking at this little triangle right here, ADE. If these three sides are the same, what do we know about all the angles? Corollary that we just did. If all the sides are the same, what do we know about the angles? Same. All the same. So A, D, E are all the same. Okay. When I look at D, C, E, is that exactly the same thing? They're all marked with single hash marks, so then all those angles would be the same. And the same in the right-hand triangle with BEC. So basically, every single segment is the same as every single segment in here. So A and B do have to be the same, but we have to figure out how much they are. If you have 3 angles in a triangle and they're all the same, how much would they be? 60. Because 60 plus 60 plus 60 equals 180. So angle A, measure of angle A equals 60. Would the measure of angle B be the same thing? Yep, because every single triangle has 60-degree angles in it. And then when you look at angle CDA, that's kind of a combination of 2 of them, right? If this one is 60 and that one is 60, wouldn't DCA be 120? And that's basically all you have. So if you ever look at a triangle that has a bunch of marks in it, but no angle measures, they're probably 60. And that's how you're going to get through it. If you don't realize there's 60, there's no way that you can do this question. So the measure of ADC is 120. Okay. We're going to do one more, and then I'm going to have you do a couple of questions on the top of your paper. Okay, suppose the triangles in problem 3 are isosceles triangles instead. So I'm going to draw this picture. Angle ADE is a vertex angle, which means the other 2 are the same. Okay, the vertex angle isn't the one that's a double. DEC, that's this one, is the vertex angle. The other 2 would be the same. And then ECB is the vertex angle. These 2 would be the same. So they're all isosceles triangles this time, which means only 2 of the angles are the same. The vertex angles are each 58. Okay, so if we have used 58 degrees, there would be 122 degrees left. And then is that split between 1 or 2 angles? 2, because we have 2 angles left, so I'm going to divide it by 2. So that would be 61. So wouldn't all the angles in there be 61? Okay, so that means measure of angle A is 61. And BCD, this one, is how much? Or how do we do it if you don't have the answer in your head? The one angle is marked 58. What's this one again? 61, so you add them. So that would be 119. So it's not always double. It depends on, the picture and what they give you. Okay, so the way that you would have done this one wrong possibly is if you would have put 58s in the A and E instead. So basically the main thing about this one is you have to know what a vertex angle is and what those base angles are. The base angles are the same. The vertex is the one that is not the same in an isosceles triangle. And I think that's it. So what I'd like you to do is, if you did not copy those down, you can do that first. And notice in each of those, I'm going to go back to the beginning. I circled the title and basically the words only. So you can look at those in your book. Make sure you get them in your notebook. Doesn't have to be today. Just make sure you get them in there before Friday, because that's when your quiz is. Your assignment hopefully will not take you very long. If it says explain, you either have to show work and how you got the numerical answer, or you have to give like a theorem number. Make sure that you are looking to use the one that's given. So if you have sides given, you're going to use the isosceles triangle theorem. If you have angles given, you're going to use the converse of the isosceles triangle theorem. If you're doing words, isosceles triangle theorem and converse of that theorem are not the same thing. So you do have to make sure you have that word converse in there. Or use the theorem number. That would be okay as well.